Assembly theory's key conjecture about the nature of life is the only physics that can generate complex objects. We need a deeper explanation of evolution in order to explain how evolutionary systems that we recognize as biology emerged in the first place.
You have disentangled the definition of life from people's biases.
That's right.
Like a chef.
I'm cooking the primordial soup.
This is Star Talk. Neil deGrasse Tyson, your personal astrophysicist. Got with me, of course, Chuck Nice. Chuck,
Hey,
baby.
Neil, what's happening?
Lord Chuck Nice.
Oh, thank you, yes.
All right, my co-host, professional comedian, stand-up comedian.
Yes.
And
Not always the same thing, a professional comedian and stand-up comedian.
and actor.
And actor.
I've seen you in some TV commercials.
Acting like a comedian. You know
Almost
what?
dropped my sandwich when I saw that.
I'm actually going to do a sandwich commercial next. Yeah.
All right, no, good that you're out there.
Yeah, you know, gotta keep it moving.
And we can say we knew you when.
You gonna know me then too.
So, wonderful topic today.
Yeah.
Oh my God, love it.
Yeah.
Love me this topic.
It's a rich topic.
So there's always been this concept of life as we know it.
Right.
And it never caught on as an acronym, LAWKY, life as we know it.
I wonder why. Such a mellifluous acronym. LAWKY.
Never caught on. Life as we know, it's like carbon-based, you know,
Right.
all the usual things
Yeah,
that you throw
exactly.
into the mix. And there's been some effort lately
Okay.
to think about life as we don't know it.
Ooh, now I like that. Is far more intriguing.
And that seems to me opens up all manner of possibilities
Absolutely.
outside of the box that we've put ourselves in.
Right.
So we have a world's expert. We have Sara. You have three names, Sara, as do I. Sara Imari Walker.
That's me.
Now, which one do we go by?
Sarah.
Sara. Okay, we'll do that.
Oh, thanks for making it simple.
I try.
We appreciate that.
I really try.
So, Sara, you're an astrobiologist and physicist, theoretical physicist. So you're coming to this life question not from the normal trackings of a biologist, because who else would you think to bring to the table when you're talking about life, if not a biologist?
Absolutely.
But now you're going to bring some physics into the equation, and I love me some physics.
Yeah, me too.
Because the buck stops at physics.
Yeah.
Okay? There's an old saying, there's no understanding of biology without chemistry,
Right.
and there's no understanding of chemistry without physics.
There you go. Somehow your subject of expertise be lords over the ball.
Lords over-
I don't know how this happened.
So what brought you to the question of life?
Yeah, I'm really interested in fundamental laws of nature and where we might find new ones. So I think this is the main motivator for me, is to think about life being explained by some universal physics we don't know yet.
Whoa.
Okay,
Whoa.
That's,
Damn, Sarah coming in hot.
It's the only way I know to go.
Sarah is not playing around, buddy.
Didn't even warm up to
I'm
that
telling
one.
you. It's like, why don't you take a couple of warm-up tosses? All right, we clocked that one at 97 miles an hour. That's fantastic.
So I can't think of a traditional department in a university that would serve this cause. And now I learn you're deputy director of the Beyond Center.
Yes, the Beyond.
That's audacious.
Now, you guys are the people that make the meat, right?
Of the Beyond Meat.
Oh, no, we
That
don't
was
make
a-
meat.
that was a joke.
Yeah, it's okay. No, we don't do anything like that. We're actually, it's like the full name of the center is the Beyond Center for Fundamental Concepts in Science. So we're actually an exploratory center based at Arizona State, and we think about deep
Arizona State
problems.
University.
Yep.
Not just in the state of Arizona.
No, not, Arizona
So
State
you're
University.
on the faculty there.
Mm-hmm, that's right.
Excellent.
ASU, they have really good astro folk there too.
Okay.
Yeah,
Yes.
no, I know ASU.
All right.
Yeah. And so this Beyond Center, are you co-founder of that?
No, the founder is Paul Davies, but I'm the deputy director.
We know Paul Davies. Yeah, an astrophysicist, like from way back.
Yeah.
Yeah.
I like hanging out with cosmologists. So, and the Beyond Center is in the cosmology, it's in the cosmology wing on ASU on the campus.
Okay, I was looking
Yeah.
at least one of your research papers. You have collaborators, some of whom are based in the Santa Fe Institute, which is also one of these beyond.
Yes.
I mean, they specialize in here's what everybody's thinking, but we're going to put a foot outside that circle.
Yeah. Now let's go beyond.
Let's go beyond.
Right.
So you're teaming up with other beyond people.
Yes. I like hanging out with people that think outside the box. They're my favorite kind of people.
In fact, some of the stuff she's been working on is not just the box. Because box is a three-dimensional object.
Right.
She's thinking beyond the tesseract.
Oh, wow. Look at that.
Now I have pretty shapes in my head. I like this.
So tell me, I know there might have been adjustments over the decades, but today, what is the commonly held definition of life itself?
The way that I consider it is that we actually don't need to define life. We need to figure out a theory that helps us derive the properties of life. So we should be able to predict features of life anywhere it should occur in the universe. So that's been my approach. It's very, theoretical physicist, need to build theories, need to explain regularities in nature.
She's got theoretical physics bad.
I love it.
It's
I do.
it's bad in you.
It's never coming out.
Yeah.
It's a little fever with you. You got a little fever. You got a little
I'm
theoretical
stuck with it
fever.
for life. Yeah, I do.
Yeah. So, I mean, basically, you're like, let's not worry about identifying. Let's find out what creates the identification.
Yes.
In the first place.
Right.
Yes.
Wow.
So how do you go about doing that?
So I started, in a true theorist fashion. I had probably like 7 or 8 working definitions, but I was trying to find, what's the commonality under them. But a lot of them were about something to do with information structuring matter was kind of the early way I was thinking about it.
Wow. Okay, I got you, because then that gets you all the way down to single cells, because even they are carrying information. So if you get to the root of the information in what creates the information, then it may not even be a cell that you're working with. It could be something outside of that.
Yep. And the cell's a good example because it's very complex and we don't think they can form outside of evolution. So the way that we talk about these ideas now, which is what I'm really excited about, is this assembly theory I've been working on with my collaborator, Lee Cronin.
Assembly theory.
It's a theory. As a theorist should do. Yeah. So assembly theory's key conjecture about the nature of life is the only physics that can generate complex objects.
Interesting.
Like a cell.
Right.
Or a microphone. Or a comedian.
We're not that complex, unfortunately.
He's very simple.
We're the simplest of all life.
Yeah. Wait, so you are declaring that rocks and crystals and things, it's not complex. So therefore, while you could, in principle, create those out of your modeling or out of your theories, that's not your target of interest.
So the nature of how we define complexity is it doesn't happen spontaneously. It requires evolution. So there are some kinds of rocks and minerals that do require, say, technology to precisely engineer defects in a crystal, like if you want a perfect diamond or something.
Right, exactly.
Or so there would be rocks maybe that pass the boundary of life, but they would be something life created or engineered.
So I love this because you poured out the mold and you said, let me start from scratch. And if you start from scratch, you're not biased by any pre-existing construct for what is or could or should be.
Right.
Now you can make almost anything that has complexity.
Yes.
And the space of complexities is then what you will study.
Yes, and that space is huge. So as an astronomical example, I like to use this molecule Taxol as an example. Its molecular weight's about 853.
Taxol, what do we do with that?
Taxol is an anti-cancer drug. It's just one molecule that's been created in a
fat
tree
molecule.
somewhere. It's a fat molecule. It's a big molecule. But if you wanted to make...
And how many atoms are in that molecule? Approximately. I mean, hundreds? Or?
And gobs.
Gobs, official
I think
term.
it's like a couple hundred.
Yeah, so on that order.
Yeah, or 100 to 200. But if you wanted to make one molecular structure of the same molecular formula, like every single 3-dimensional conformation, it would fill a volume of about 1.5 universes. Just one molecular formula. 1 molecule per centimeter cubed. This is how big chemical space is. The reason it's hard to make complex objects is there's so many of them. So evolution is necessary to select in that space. So we can't have a universe and a half full of just Taxol. It'd be very boring.
Right.
We live in a universe with lots of different complex objects.
Wait, let me repeat what I think you said.
Yeah.
That the complexity of, what's it called again?
Taxol. It's not a special molecule either. I just picked one out of a hat.
Yeah, we all have these in our hat, don't we?
Yeah, I'm carrying around a hat with lots of Taxol in it.
So what
more like a ski mask.
If I think I understand you, the complexity of this molecule is such that if you explored all molecules that could be that complex, there's not enough room in the universe to contain
hold
them.
it.
That's right.
So clearly, that molecule's existence comes from some prior requirement or
for that
urging
configuration.
For that configuration.
Right.
That's exactly right.
That's fair.
Yes, that's exactly right.
Man.
So let me ask you this then, because now I'm a little. You'll have to forgive my ignorance, but I'm the only non-scientist here. Thank God. So I can say stupid
God
stuff.
had nothing to do with that. Okay, but go on.
That's a very complex molecule. Okay. Anyway.
All right.
Okay. Where exactly does spontaneity and selection cross, and how do you identify which is which? Which is
I love this
which is a
question.
progression and which is a cross
Yeah. So,
pollination?
the kinds of very simple molecules that might happen on a planet, can happen spontaneously. Or if you're thinking like Lego are easier for people than chemistry, if you have like a tray with a bunch of Lego in it and you shake it, you're going to get some Lego sticking together and making simple shapes. So those would
Okay.
be spontaneous objects. But you're not going to be able to shake it long enough to have Hogwarts Castle spontaneously emerge out of it. That would require a process of evolution and refinement.
And
building.
a wand.
And a wand,
Okay,
yeah.
go ahead.
No
Especially the
magic,
wand.
though. The universe doesn't have magic.
Oh.
At least not in this scenario. So,
She's covering her
I
bases.
know. She's like, you know what?
She's
because
in a Beyond
she was
Institute.
like, I am a theorist.
No, but she's in the Beyond. You got to leave room
Yeah,
for the
gotta leave some
magic.
room. Right.
For the wand.
Go ahead.
well, I like, magic for me is yet to be, regularized in theoretical physics. So there still always has to be other things for us to do.
Any sufficiently advanced technology is indistinguishable from magic.
That's right.
Yeah.
Or the laws of physics.
Good.
Wow. Okay. So go ahead. Back to you can't get to the place of where you could shake it and then have Hogwarts. So
So if you
Yes.
do shake it and some
some
stick
stick
together,
together.
those are like the amino acids.
Yes.
gotcha.
Yes.
Because we did
Yes.
we did that with the Miller-Urey experiment,
That's right.
where he just throws
Yeah.
some basic.
Oh, can you explain that, please?
Everybody knows that Miller.
Clearly they don't. Okay. And by the way, of course I know. I'm just talking about the people out
No,
there who don't. I mean, there may be someone
Please
listening.
regale us of
Yes,
the
please tell us
Miller-Urey
about them,
experiment.
yes.
Yeah, so Stanley Miller was a PhD student. I think he published a paper in 1953, so it was a long time ago. But basically, he put a bunch of molecules that might have been available on the early Earth in a flask and put some lightning in his flask and tried
As
to
a
model.
source of energy.
Yes, as
Right.
a source of energy, and he had a reducing environment, and then he got amino
Reducing
acids
means
out
you
of it.
remove
Yeah.
oxygen is taken out.
Yeah.
uh-huh.
And so he made amino acids. And, people were so shocked by this at the time. They thought little aliens were being crawling out of, life forms would be crawling out of the test tube in a couple weeks. But that's not what happened,
Right.
unfortunately.
Yeah.
The reducing environment is that we think the early Earth did not
Not
have
have
free
a lot of
oxygen.
oxygen.
Right.
Right.
So he's trying to, if life's formed on Earth under
Well,
these conditions.
you got to create the conditions
right.
under
And
which
so
it
what,
formed.
so what came, so out of the ooze, nothing crawled out. But
Nothing crawled out. If you run the experiment long enough, you basically get what we call a TAR in prebiotic chemistry, which is just an undifferentiated mess of a whole bunch of organic molecules that we can't identify.
Gotcha.
Okay, prebiotic chemistry means what?
Prebiotic chemistry means chemistry that could plausibly happen on the early Earth in the absence of life,
Before you have life.
before you have life.
So it's organic chemistry.
yeah.
Right. Or-
Yeah, I like the word organic chemistry better because prebiotic kind of makes it sound like it's predisposed to become biological, but there's no teleology, there's
it
no
also
direction.
makes it sound like something you
Yeah.
take before a meal.
Yeah,
Oh,
that's true.
prebiotic?
Yeah.
People do confuse it with probiotic all the
Exactly.
time.
Oh my gosh.
All that probiotic chemistry.
Wait, I got something here. Here we go. You want something?
Oh, right.
This is-
Oh, you have the primordial soup. That's so adorable.
Yes, I have a little can of primordial soup. Okay, and so in an emergency, if we got to jumpstart life,
Right.
just come back. We can make that happen.
Amazing.
Yeah.
Amazing.
As you can see, Sarah Walker's research and those astronauts stranded in space help us critically think about the origin of life and future of humanity. But with recent advancements in technology, we might not have to worry about human extinction after all. Scientists have found a way to store the entire human genome in a near indestructible 5D memory crystal, enduring extreme temperatures, pressure, and cosmic radiation for a smooth journey through space. When it comes to groundbreaking developments that challenge our understanding of existence, it's important to see how different scientific sources are interpreting the research to fully understand it. Luckily, our partners at Ground News make this much easier to do. With their Vantage Plan, you get access to original reporting plus insight on every article covering it. Ground News provides this level of critical analysis for every topic you're interested in, using patented technology that helps us see important perspectives we might have otherwise missed. Head to ground.news/StarTalk or scan our QR code and save 40% on their top-tier Vantage plan today, making it only $5 a month for unlimited access to infinite knowledge and credible research. We can't recommend Ground News and their commitment to rigorous analysis enough. Now, back to the show.
So, all right, so I like the basic principles that are being invoked here. Very, very simple.
Yes.
Basic principles. Okay, so now you shake the Legos, some stick together. Now what?
Now selection needs to happen to get to something like Hogwarts, which means that some parts have to start being, abundant in the environment and then reused to build further structure.
All right.
And these become your units of your building units.
Yes.
Your bricks.
That's right. Yes.
To build the edifice.
Yes.
And you say selection because they are selected to succeed? Is that the idea?
Yes, and also because selection is excluding that huge space of other possibilities. So
You have to,
every
otherwise
step,
you're lost in
Yes.
space.
That's right.
Yeah.
I don't even want to know how many possible configurations there are of the Legos in the Lego Hogwarts set. It's like 2,000 Lego. If you imagine all the things you could build out of that, it's crazy.
That's three universes.
Yeah,
So
at
now,
least.
so now, since you're looking for life outside of this, let's consider in the selection
Wait,
that
life outside of what?
I'm saying outside of the life that we know.
Oh, yeah.
Right.
Yeah,
Right, you're looking for life outside. So,
Other planets even.
so let's go back to the primordial soup of another planet, and we have the shaken Legos. Okay, but are there circumstances that maybe led to selection for the development here that may be different there, creating something different entirely? Could that possibly be the case?
Yes, I think so. So I think assembly theory would predict yes, because the possibility space of the chemistry is so large. And what we've actually been able to do is define a threshold that we expect life to emerge, which is what you described as this spontaneous to selection dynamics. And it actually has, for the physics nerds out there, it has like properties of a phase transition, right? So you go from random configurations of objects to selected ones that have this historical pathway.
The phase transition is all the molecules are this way, and then like a moment later, they're in a whole other way.
Configuration?
Yeah. So, but we live this.
Yeah.
Right.
Okay. We it's our fancy word for it, but when water becomes ice.
Ice. That's
Ice is
that's
not
a phase,
water.
Right.
That's a phase transition.
Exactly.
When water becomes
Steam.
it's a phase transition.
There you go.
And so we actually generalize that term even in the early universe. If if there's everything is this way and then something happens and then it's another way, we just call it a phase transition. Gets us through.
And we geek out on that.
Yeah. Yeah,
We
'cause-
physicists love phase
Almost
transitions.
anything can happen through a phase transition.
Right.
That's right.
And like spooky things, fun things,
Yes.
dangerous things.
Yes.
So I
Go ahead.
shake the Legos. Some of them stick together. They're the Lego counterpart to amino acids. This was done in the Miller-Urey experiment. It's amino acids, which are the building blocks of protein, the building blocks of life as we know it.
Right.
All right. On another planet, you shake it, we're thinking it'll also make amino acids. So this becomes a unit of life, let's call it that, or your AI, what's AT? What's the
Assembly theory, AT. We talk about assembly index as the number of steps to make an
Okay,
object.
so that's a step.
Yep.
That's a step.
Okay.
If that's the same step everywhere,
Yep.
then that greatly limits what comes after, because you're not starting. Not everything is possible in that early first unit.
Yeah,
right?
this is a great point. The interesting thing there is how varied geochemistry is on different planets. And actually, even if you look at amino acids, there's hundreds of them that we've identified in meteorites.
Right, and not all of them.
yeah. Not all of them are in biology.
Right. So if you find them in meteorites, it means they're
out there.
They're out there.
They're being
out-
made.
They're being made.
But they're not here.
Or even if they come here, we're not using them.
Well, right.
Right.
They don't serve a purpose here.
Right, exactly.
Right.
Okay,
That's
go on.
the point.
Mhm.
Yeah, so I don't think that we should have an expectation that all the steps on the pathway to something as complex as cell would be the same. Because, maybe the first few are similar, but as you build up the complexity of the chemistry, there's so many paths you could take, so many kinds of molecules, that there should be a point where planets start to diverge in what kind of biochemistry evolves out of the geochemistry.
So let's. Okay.
Aliens can be really weird.
That's what I was going to. That's what I was going to get to. It's like it sounds to me like a virus could be an alien, like highly effective, like lots of information, carrying out like purpose, procreating. I mean, if you can look for something like that, how do you even begin to narrow the search once you start looking out there?
Yeah, so the great thing about assembly theory is we can actually measure how assembled a group of molecules is with
Quantitatively.
Quantitatively, we have predictions that we can make from the theory, but we can test them in the lab. And so we have a way of measuring the complexity of a molecule independent of knowledge of what the molecule is. And we can just do it with a mass spectrometer.
Okay.
See, this is physics,
wild, man.
badass
I
physics
love it.
coming in the doorway here.
Yeah.
All right. So,
We like measurements. They ground us in reality.
right. Evolutionary steps, sometimes we think of them that way, can involve added complexity. So what are you doing that's different from that?
So evolutionary theory as we have it now works really well for biology on Earth, but it doesn't help us understand life on other planets or solve the origin of life because we don't know where life comes from to begin with. So we need...
Because you have a sample of one.
Yeah, we have a sample of one. It's a
Okay.
big problem. We need a deeper explanation of evolution in order to explain how evolutionary systems that we recognize as biology emerge in the first place.
Is there any chance that it could just be a mistake?
You know, that might be true, but then it's not very interesting from the perspective of theoretical physics because there's nothing to explain.
Okay.
Good
Yeah.
answer.
Yeah. I mean, it doesn't stop the search, though. But
No.
you're right.
That's a good answer.
It's not very interesting at that
All right,
point.
so let's make sure we're on the same page here. When I think of how a biologist would define life, which there's been variations on that over the decades, but what comes to mind is it's something that has a metabolism, so it uses energy from its environment, it reproduces and it evolves in a Darwinian way.
Yeah.
You have things to add to that, subtract from that?
I don't...
Or can you juxtapose both? What do you call what he just said from where you are? What is that? And then where are you different?
So one definition that people like to use, which encapsulates what you're saying as like fundamental pieces of it, is life is a self-sustaining chemical system capable of Darwinian evolution. It's quite a mouthful.
That is what he just said, though.
Yeah, it is exactly
That's
what he
exactly
said.
what he just said.
Yeah,
It is.
it totally is. So, there's a lot of problems actually from my perspective with that definition. One of them is whether you regard life to be self-sustaining. So viruses are an example. People don't know whether to place them as life or not. Because they're not self-sustaining on their own. And in fact, when we're doing, chemical evolution in the laboratory, like trying to study molecules, we don't know how to call them alive because they're not self-sustaining because graduate students are pipetting, like they require the graduate student.
Pipetting, that's a verb.
Yeah,
I know the pipette.
Yeah.
It's a little thing.
Yeah.
Yeah.
Put a little glass straw in there.
Yeah. So
Yeah, you gotta move the molecules from one tube to the next to do artificial
So why
selection.
you do it? You say, I am crushing your head. No, okay, sorry.
Right. So there's many, or my favorite example is like, a parasite that, sits in the brain of an ant and, pilots the ant.
Right.
Right. So I talk about that example in my book,
I love that parasite, by the way.
It's so crazy.
Yeah.
But is that a life form? Because it's actually, it's a symbiont, right? So, or actually a parasite. So this idea of self-sustaining is kind of very problematic for a lot of reasons. I don't actually think life is defined by chemistry. So this is, again, getting at deeper physical principles.
Wow.
So I include technology.
blood drawn there.
Yeah.
Right.
yeah, first shots fired. Yeah.
Yep.
Okay.
Yeah. So my definition, my understanding of life, I don't have a definition. My understanding of life is the things that can only be produced by evolution and selection, and technology is also an example of that, and that's not chemical.
Right.
And also this idea of it being self-reproducing. I mean, there are plenty of humans that can't self-reproduce. Actually, no human can individually self-reproduce.
Right.
I've been trying.
But there's plenty of things.
I've been trying.
Yeah.
But a mule, for example,
Yeah, exactly.
is certainly alive.
Exactly.
Right.
Can't
Right.
reproduce.
Can't reproduce.
Yeah, and those are kind of odd examples because we bred them. But even if you think of like a bee in a colony, right? Like most of the bees can't reproduce alone. Are they not alive?
Right.
Because they're part of a social
Right.
network.
Okay,
So
the traditional definition of life have issues.
lots of issues.
Plus-
Every single word.
But plus, there are stars that have metabolisms and they live out their lives and die, and then they explode and send their materials to other gas clouds that make other stars.
Right.
So they do reproduce.
And there's
Right.
some heritability there because of the elements that get made in one star
The
generation.
DNA of one
Yep.
star goes in another
Yep,
star.
that's right.
So are stars alive? Right. We can
Yeah.
ask that question.
Yes, we could.
So
Can ask any question.
So why even have a definition at all?
So I think definitions are useful heuristics in the absence of having a more fundamental understanding. And so one of my favorite sort of analogies that people in my field make is like, how would you define water before you knew atomic theory? You would describe it as like a clear liquid. It might, be a liquid at room temperature, but you wouldn't really understand what water is until you understand what atoms are and how they combine to make H2O. And that's sort of where we are with definitions of life. We can kind of describe effectively its properties, but we don't
like
have
a macroscopic.
Yeah.
You know what you're looking. You know what you're looking
account.
at. You just don't know really what it is.
Yeah, that's exactly right.
Right.
And
Wow.
I want to know really what it is. I want to know at the same level that we understand our other theories of physics, like gravity or quantum mechanics.
You have disentangled
Yeah,
the definition of life
Yeah.
from people's biases.
that's right.
Like a chef.
Yeah,
Like when
I'm
they
cooking
talk
the primordial soup.
No, when they deconstruct
When they
it.
deconstruct the dish.
Deconstruct the
Yeah,
dish.
you see all the. You're like, what the hell is that?
I know, right? I had eggplant parmesan. The eggplant's here. The cheese is over there. I
right?
say, dude, what am I paying
Exactly.
you to do?
The Parmesan shows up on Tuesday.
All right, so let's get back to this. Any good theory?
Mhm.
In fact, I'm a theory snob. Okay,
Ooh.
Excellent.
forgive me.
I love
dear.
that. No, it's
No.
okay. I'm also a theory snob.
No, theory snob. In the
Please
sense,
tell me about your
But
theory.
I want to know what your definition of theory snob is. Yeah.
I'm not sure that's a very good theory at all. That's not
snob.
the kind of theory that we would let into this club. Yeah, dear. Who sponsored you? Sorry. I'm
No, I
sorry.
like it. It's good.
If you have an idea that you're still testing,
Mhm.
then we should call it a hypothesis.
Mhm.
Hmm?
And once it's tested and verified and supported by multiple people, and not just your lab in the Beyond Institute or the Beyond Center, then it can elevate to the level of a theory, which gives us the thermodynamics theory,
Mhm.
quantum theory, relativity theory. But it's not Sarah's theory until it's multiply supported.
Yes.
I would call it Sarah's hypothesis and your colleagues, your hypothesis.
Ooh.
Am I allowed? Will you grant me that?
I'll grant you that. I think there are clear reasons why we call it a theory. And for me, what theories are explanatory paradigms, like they're actual frameworks that have broad
But you also
explanatory
have to
pattern.
predict
Yeah.
something that we have found. What have you predicted that we have found?
We have predicted that there should be a threshold above which only molecules produced by life should reside, and we've tested that experimentally.
Wait. Say.
I missed that.
The universe can generate simple molecules. It can't generate complex molecules without evolution and selection. That suggests a
This
boundary.
is the Lego experiment.
Yes,
Right.
a boundary that just random chemistry can explore, but it can't go beyond.
Oh.
And we've tested that with living and non-living samples, and even some that NASA sent, and this was done by Lee Cronin's lab. They sent him samples and they blinded them, and they tried to a blinded sample is one that you don't know the identity of the sample, and they tried to really trick them. They sent them Murchison meteorite, which is one of the most complex inorganic, non-biological samples in the solar system, and it's still classified. The experimental approach still classified it correctly as non-living. And what we saw was only the living samples had an assembly index value, this number of minimal steps above 15, which is not a magic number. It's just an experimentally confirmed number.
So you're suggesting that nowhere in the universe, without some other driving
Force
forcing on
behind
the
it.
system, would give you a complexity higher than this.
About 15, but that was for a specific set of chemical kinds of bonds that can form. So we don't know if 15 is a universal number. It might be
Right.
different in a different planet with different geochemistry.
But the threshold is there, is
Yeah.
the point.
So that was the first prediction that we've made that we've tested. And also the other thing that we have that hasn't come out yet is actually constructing phylogenetic
Come out,
trees.
hasn't been published yet.
Hasn't been published yet.
Uh-huh.
Constructing phylogenetic trees with no genomic information, just molecular information.
Taking that stuff down to molecules.
Molecules.
Damn.
Molecules contain their history.
Damn.
Wow.
But I think your point is really important about a theory. And obviously, this theory is still under development. But I think theories have played a really important role in the history of physics in terms of trying to unify a broad set of phenomena that we
Of
thought
course.
were different.
Yeah. Initially, I would just call them hypothesis.
Yeah, I think
That would then later be elevated to theory once it has been verified.
Yeah, you should kind
Yeah.
of drop it down to hypothesis, because then when it's elevated, we can call it Sarah's theory.
I don't want it to be called Sarah's theory,
No,
though.
I'm saying.
Wait.
What do you mean you don't want it to be called Sarah's theory?
Wait.
Of course you
What
do.
it does is, speaking as an educator,
Yeah.
what it does is it protects the usage of the word theory for things that are experimentally objectively true.
Right.
Yes.
Otherwise, you get people in Congress, I quote, "We should teach evolution only as a theory and therefore teach other theories as well."
But evolution. Oh,
It was trying to get God in there.
Oh,
right.
God.
And so we're susceptible.
Right.
Yeah.
If a theory is something that's sort of in progress and not really sure yet, and then it gets shown to be false, people will say, well, we're waiting for the day that relativity theory is shown to be false. But that's not
Yes.
going to happen.
Yeah.
Right. So it's a.
I know, I understand that. I think working from the scientist side of it, it's really interesting because I think also I've noticed that, distinguishing between a model and a theory is hard.
That's another one. Yeah.
Yeah.
So this is on some level it's semantic,
Yeah.
but it's semantic it makes my job easier if we get the semantics right.
We want your job to be easy.
Don't mess with my trying to do it. So again, you're telling me left to its own devices, the universe can construct molecules of complexity level 15 in your units of complexity
Yes.
Paradigm.
Yes.
Okay. After that, what does it require?
It requires a system that has some constraints on what kind of molecules get produced.
That favors one kind or another.
Favors selection.
Selection.
There's
And
that
so
word
we're
again.
We're back to that.
Okay.
I gotcha.
So,
And memory.
whereas getting to a complexity level of 15 does not require that.
That's right. And so a key component of passing that threshold is actually storing memory in the system because you have to remember the steps.
Mm-hmm.
So you can get to it every time.
Right.
That's right.
Oh, otherwise it's just randomly getting
That's
there.
right.
Right.
Oh my gosh.
Yeah, that makes sense.
Oh yeah.
Yeah.
So
You have to know what not to do in order to
Yes.
know what to
So
do.
you're saying this meteorite and this meteorite can both get to complexity level 15 because they both formed in the void of the early universe, of
Yeah.
the early solar system, but without a driving force.
Yeah, without something to remember molecules that the meteorite has made in the past and then build further complexity on top of that. Can't do it.
So now you need a system to store information.
That's right.
And DNA can do that.
Yes.
Famously.
Yes.
So well, I guess there's no way to know. I was going to say, is DNA, because like all of everything around us, that's organic, we all share this, right? So is that optimized in any way for life? Do we look at that as a model
Well, I
that
like
is
that.
optimized?
I like that.
Yeah.
Because the Murchison meteorite doesn't contain living molecules.
That's right.
All right.
Yeah.
So if you're going to get what anyone would call life, why doesn't it select the same path? Because this is a question that's come up. My colleagues in geology posed the question, and I didn't have a good answer. It was an intriguing question. They look at multiple planets and they're finding the same rocks. This comes directly out of what you're saying. They find the same rocks, even though it's a completely different planet.
Yeah.
Same rocks. That is, they understand the rock chemistry of what they
composition,
form,
right.
the composition and the like. There's basalt there. There's basalt here. Okay, that came out of a volcano. Volcanoes here, volcanoes there. Why can't life have the same consistency that geology does?
It's because of the complexity.
Well, see, that you have an
Yeah.
answer for that.
Yeah.
You come out of your assembly theory with an answer to that.
Yeah. Yeah. That's right.
Can you assemble something like DNA that isn't DNA? That would be
Yes.
That would
What? Watch out! Hello.
Okay.
Oh, so
sorry.
you buried the lead.
Okay.
Sorry.
Oh my God.
Okay. Sorry.
Okay.
All right. So
That's amazing.
what, pray tell, can store information for you and go beyond your 15 steps?
And
That is
do you have this thing locked up?
that's it.
That is what
I
I'm.
have to say, I'm a theorist, not an experimentalist,
Okay.
so I haven't built these things myself. But even in the space of just synthetic biology, people have alternatives to DNA and RNA, which are the usual.
Let me just remind people, synthetic biology is basically genetically modified organisms.
Yeah.
Right. That's what that
Yeah,
is. It's got this
exactly.
new branding, but that's what
Yeah.
we start out thinking about it as GMOs.
Because nobody wants to say genetically modified anymore.
Yeah, so synthetic biology.
Yeah, so there's all kinds of different. They're called XNAs, like alternative nucleic acids, basically that people have studied. So those are real molecules that people have validated in the lab and actually work in living cells. But what we're trying to get at, that's a bit deeper than that with assembly theory, is actually looking at the iteration of chemical space and trying to predict what molecules could be. And right now, where we're doing that most significantly is for drug design.
That makes sense.
And predicting pharmaceutical drugs. And there are some approaches also, if you're talking about validation of a theory, there are some places where we've been able to predict molecules and actually synthesize them. And then
Knowing that they'd be stable.
Yeah.
And
So, for example, one place is really interesting is looking at non-addictive opioids.
Right.
So if you want to make an opioid, you want to keep the opioid groups,
Right.
like those parts of the molecule, and then make it non-addictive. You actually have to look at molecules that are not addictive and then try to combine their features.
Well, you get them together and then you figure out how
Yeah.
you make the non-addictive molecule bind in such a way that
Yeah.
you get the result of the opioid without.
Yep. So you can look at the steps to making both kinds of molecules, and then you can combine those steps to look at other kinds of molecules.
Freaking
I
crazy.
know. Okay, so how? So
This is what solving alien life will give you: new
Oh,
drugs.
we're gonna get to aliens in a minute. That's good.
Let me tell you something.
That's good.
Make sure you lead with that when you're going for your grants.
It is part of the strategy, actually.
I'm telling you,
It is,
it's a good one.
Yeah, how
It's
the
a good one.
molecules behave. So, give me an example of something that can encode, store information that is not DNA.
Well, you can store information in RNA and protein. Those are already in cells. But there's one I like is, and I actually don't know if people have stored information in it, it's called PNA. It's peptide nucleic acid. I like that because it's kind of a cross between a protein and DNA.
Right.
All right.
And so most of the places where people study these kind of alternative nucleic acids is just, in synthetic biology labs. But there's a whole host of them that you could use. Just the same way that you can store information in DNA, you could just write a sequence of bases in one of these kind of molecules. Minerals are more fun, though. Trying to store information in a mineral is pretty crazy.
Whoa. So, okay, that's pretty wild. Now, why would you be storing information in the mineral?
Minerals are really important in origin of life chemistry, and we think that they were actually the first templates for information to actually pattern chemistry in specific ways, and they retain, they have an aperiodic pattern to them, which means they can contain a lot of information. And they
Because
actually,
it was perfectly periodic.
Yep.
There's hardly any information.
That's
there.
right.
Right.
Yeah, so
Right.
this goes
Like
all
a
the way back
crystal
to,
has hardly any information.
Right.
Right.
Because everything is regular.
yeah,
Right. So if it varies but then repeats, you can
yes,
stick something in there and
Right.
repeat
Yeah.
it and remember it.
yes.
Okay.
Fascinating.
Yeah, so minerals might have been the templates for the first genetic information, actually.
Gotcha.
Yeah.
Gotcha.
Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with Star Talk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't
All right.
happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh.
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up. So now we want to look for aliens.
Mm-hmm.
How did what you do inform that?
So the current way that we're informing it, I think that's most significant, is this ability to look for complexity in the universe as a biosignature instead of looking for specific molecules that life on Earth generated. And we can do that with a mass spectrometer. So we can just, fly to another body in our solar system and try to infer whether there's high assembly molecules there.
Right.
Whether or not it's crawling out of a beaker.
Doesn't make a difference. Or
Well, we haven't seen that yet. And we haven't seen little critters crawling around on, Enceladus's plumes or on Mars or anything. So I think we need better tools.
In your universe of complexity, it is a measure of the complexity of information. And artificial intelligence is a level of complexity that's even beyond what we think of as biological. How do you rate artificial intelligence as it's currently expressed in our world on your scale of
So I definitely think artificial intelligence is life, but I also, I know,
Okay.
shocking, huh? Shocking.
What?
But I also think your
Why
microphone.
was I programmed to
Yeah.
feel pain?
Oh, did you feel pain from that? I'm so sorry. I didn't mean to induce pain. Often, there's a lot of shock value to things I say. So I guess I induce pain.
That's
a
a
lot.
very shocking statement. Why? Why do you feel that way, though?
Well, so I think you want to make a distinction between what you might call life and what you might call alive. And this actually comes derived from the theory and the way I've been thinking about life for a long time. So the things I would qualify as life are anything that requires evolution and selection to produce them. And artificial intelligence do not exist on a planet unless there are billions of years of evolution to make intelligent beings like us that are capable of engineering them. So in that sense,
But
they
the
are
universe
life.
is not creating AI.
Right.
No,
Exactly.
there are no large language models on Mars unless we put them there.
Right.
Interesting.
So therefore,
Yeah.
we are the remembered
Yes.
molecular complexity
Yes.
to create that.
Yes, we're like the minerals imprinting on the genomic information of the
that
AI.
makes sense.
Man.
I got to say, I didn't want to actually agree with this, but now I'm thinking of perhaps in a world, maybe even our own, where we're a couple hundred years in the future, or we have somehow mucked things up to the point where we're not going to be here. So we then turn to artificial intelligence, imprint it with the ability to do everything that we do. It continues to evolve in our absence. And then somebody comes and finds us, but not this organic life. It finds us in the form of what we left behind, which was artificial intelligence.
Okay, what have you
Yeah,
been
I don't-
smoking before you came?
I have a more
You just
optimistic
created
view
a
of
whole
it, though.
story.
I
there.
did create a whole
Okay.
story out of that, and it
I-
wasn't very optimistic, but go
Yeah,
ahead.
I think when people envision that future, they don't envision us still being here. But cells are inside our bodies and part of like the evolutionary structure we are. They've been here for billions of years. I don't think artificial intelligence or our technology is going to replace us. It's going to become part of a larger integrated system of technology and biology that's co-evolving on the planet.
I
So,
agree with that as a beginning, but I think unfortunately our nature
Oh, when
is
we get
our
off
penchant
planet.
and proclivity for self-destruction, which will leave artificial intelligence behind.
You're a glass is half empty. I'm a glass is half full kind of person. I
Let's
guess.
take it to the next level.
Go
Yeah.
ahead.
Okay.
Go ahead.
Actually, I have the answer to the half empty, half full question.
Excellent.
Yeah. Drink it.
What is the answer? That's a profound question.
No. To me, it's no longer profound. If you have a vessel
Uh-huh.
and you're adding liquid to it,
Right.
and it reaches the halfway point, it's half full. If you have a vessel
Oh,
and
you
you're
have to know the
removing liquid
mechanism.
from
I
it,
see.
It's half empty.
it's half empty.
So it depends on where you start.
No, it depends. The rate of change. So it's the like in calculus would be the first derivative of the volume of liquid that's in it.
Right.
Is that positive or negative? And then it's half full or half empty.
Right.
History matters.
Yes,
Yeah.
exactly.
It's very
you go.
assembly theoretic and very evolved.
Thank
Wow.
you. See?
There you go.
See, I just got a compliment.
Yeah, you did. Don't worry. I caught the compliment.
Okay. All right. So let's take it up a notch. If we are all simulated by some alien
not.
juvenile in a basement,
Yeah.
well, they just simulated you to think and say that
Sure.
in that full up
Yeah.
variant.
Or simulated a surrounding where it would lead you to say that, even you being sentient and capable
That's
of
what I'm
making
saying.
deductions.
That's
A
right. That you would
simulation
just-
would say something like that.
Oh,
It's exactly what you would say. So
that was very good.
that was good.
That was good.
So a simulation is zeros and ones
Mm-hmm.
on a chip,
Mm-hmm.
creating information
Mm-hmm.
that's stored in zeros and ones and manipulated and maneuvered. Is that alive?
So simulation.
Are you alive in a simulation?
Oh,
I don't think that we're living in a simulation. And the sort of key evidence there is you just talked about the simulation having to run in a chip, which means it needs a physical hardware. And there's always a physical substrate underlying any simulation that, as far as we understand, so there's always a physical reality at the bottom.
Why isn't the simulation empowering you to discover molecules that comprise
It
your body?
does. It does actually, because you can have AI-driven exploration of chemical space,
Yes.
for example. So that's a clear
Absolutely.
place where a simulation is driving
Right.
exploration and making things physical that aren't physical in the absence of a simulation.
Exactly, because we joke about,
Yeah.
we talk about if this whole world is simulated, it would be really inefficient to simulate parts that no sentient being is absorbing at any
Exactly.
given moment. So you'd only simulate where you need
what
to
is
simulate
necessary,
what is necessary
at the time that it's needed.
So if I want to dig to the center of the earth,
I don't need to make it until I'm
Yeah.
getting to the
until you
center of
dig
the
into
earth.
the center of the earth,
Right.
and you simulate it as I'm doing it.
Yeah.
And so the simulation is creating the molecules that I'm measuring as having complexity.
I think we see observational evidence of that, and just with our technologies. And I think that's really important. And I think there it's explanatory. But when you say the universe is a simulation, I don't think it gives you any additional explanatory power. I find it to be a useless hypothesis.
Well, I know what you're saying, because then everything is resolved. It's like I say.
She just called me useless.
No,
I'm just kidding.
No, what I say to that is it doesn't make a difference, because at the end of the week, I still owe Visa, $210. So what difference does it make if the whole universe is a simulation, if at the end of the week, I still owe Visa $210?
And you can still write down like laws of physics that describe your universe.
No, that's what I'm saying.
So
it doesn't make a difference. It's all the same.
Oh, I understand it. You're
It's
saying the distinction is not interesting if you can't make the distinction.
That's right.
So
I think simulations being an emergent property that the universe creates, the one that happens through evolution, is interesting. And then asking about the physical nature of simulations and why life generates them. That's interesting. Saying the universe is a simulation kicks the can way too far back for me to give any explanatory power to what we're talking about.
Oh, so because you can't figure it out, it don't mean nothing.
That's exactly right. Don't you know you're in a room with theoretical physicists? That's exactly that's my card.
We'll grant you your complexity.
Okay.
In your assembly theory
Thank you.
Universe.
How magnanimous of you.
I know.
We grant it. Star Talk grants you assembly
Do I
theory.
get a badge for this or something?
I'll find something here. Hit on you here.
I love this.
Or
I'm like knighted.
So in that, does it say anything about free will? We've had a few episodes on that subject with some leading thinkers in the area.
Indeed.
Can you say anything about it?
Yeah, I have a lot to say on it, but I think the sort of most important thing is I think you can have free will and be consistent with the laws of physics as we understand them. And the reason for that—
You can have free will.
You can.
Because people were arguing that you couldn't.
Yes.
Because the laws of physics are commanding everything you say, think, and do.
That's right.
Yeah.
And then the flip side of it is the universe is totally random and then you have absolute freedom, right? So it's not that you have total free will is a trade-off between the sort of control and the freedom. And I think what happens is when you have these evolved structures that are building complexity, they become really constrained by their history, but they still have some freedom in terms of the kind of complexity they can generate. And so, and this becomes sort of deeply intrinsic to what they are. So they are deterministic in some sense, but there's still some freedom for them to actually make action.
Normally when we think of free will, we think of I'm deciding.
Right.
But really, if you come at it from a molecular point of view, it's whatever the molecule is going to make. And it'll work within the space of options it has available.
Yeah, free will is executed over time, right? So this is also the thing, it's not instantaneous. We don't have free will to be in Arizona right now,
right?
But we could be there tomorrow.
Mm-hmm.
So I think this, a key point that we're missing is it's not like you have instantaneous command over what the atoms in your bottom are doing, but you can make decisions over time.
And even your decisions are determined by what came before. So they're executed over a period of time.
Yes.
Just the fact that, I'm a comedian. Well, I didn't just wake up one day and go, I'm a comedian.
Yeah, it has precedent.
It has precedent, right. So that makes
assembly
sense.
theory makes some really radical conjectures about the future being larger than the past. And so there's also some freedom in terms of, because of this idea of building complexity, the future is always more complex and larger in sort of the space of possibilities.
Well, that's because it's not here, though.
Yes.
I get this, and it helps that we have an expanding universe.
Yes,
if
it does. Exactly. No, this is exactly right. The universe is getting bigger every minute.
To accommodate
exactly
this.
Cool.
What does this say about entropy?
So,
entropy requires—
I want to hear this.
You're not going to
Hold on.
He's getting his popcorn out.
Let me get my popcorn out.
He's gonna.
After all that we've been through, we got the entropy. Now I got to hear
entropy wants disorder as a direction in which systems move.
That's right.
All right.
But the reason that we describe things that way is because of the way we label states. Like entropy depends on a couple key features. One is you as an observer labeling the particular configurations, and the other one being able to talk about an ensemble of systems that are identically prepared and there's some statistical trend. And what is happening in the biosphere is complexity is increasing. It's kind of like an entropic tendency, but it's actually over configurations, like the combinatorial space. And so I don't really actually think the second law is telling us that things are—
Second law of thermodynamics.
Yeah, second law of thermodynamics is necessarily telling us that things are trending toward disorder. I think there's a deeper law underlying that can also account for the structure of what we see in life.
But
Of course, there's still entropy, on the
typical
boundary.
physics would say
Yes.
we're getting, it's only for closed systems that you evolve towards a higher.
But of course, the universe might be an open system.
No, but I'm saying, but Earth is clearly not a closed system.
That's right.
We have sunlight coming in.
That's right.
And so we've credited that infusion of energy as a pump for the development of complexity.
Yes.
That wouldn't otherwise be there.
Right. Like if there were no sun, none of this crap would be here.
But one of the things that's been really hard from the perspective of theoretical physics as it's written now, not like what new laws might be present in biology, to explain is that it looks like the what life is doing is changing the nature of the underlying state space as we talk about it in physics as it's going along. So it's hard to define something like entropy when you can't count the same things at every instance in time.
So you want a second and a half law of thermodynamics that applies to the observed universe.
The second law of thermodynamics is an approximate law. I think we all know it's a statistical statement. I would like an exact law.
Ooh.
Wow, you were very demanding, I gotta tell you. You are not messing around.
No. Theoretical physicists don't mess around.
Wow, okay.
Screw you, Newton.
It's all his fault.
And you put all of this in a book. There's a book.
Man.
Oh my gosh. Life as no one knows it. Except for you.
I still don't know it either. I'm still one of the no ones.
I love it.
Life as no one, including the author, but it's the whole foundations of that thinking.
Yes.
And I'm glad it doesn't just live in this conversation.
Yeah.
Because it lives in the pages of this book. So this came out just recently.
That's right.
Just summer 2024.
Oh, good for you.
Yeah.
Congratulations.
Thank you.
Congratulations. Your first book?
It is my first book.
Excellent.
Wonderful.
Excellent. And at the rate you're going, more books should be on.
Are you kidding me? We just wrote one today. We wrote one just now. Are you kidding me?
No, so I look forward to what becomes of this branch of thinking.
I'm hoping we